Thank you all for joining us. Today we're going to be talking about making strong, consistent parts with hot plate welding. My name is Jason Dornbos. I'm an account manager here at Extol. My co-presenter is Catherine Urives. She's an applications engineer. She works in our process development center where we use these hot plate welding and other welding technologies all day, every day. So, as you can tell, we have a chat and we're trying to, pay attention to that throughout the whole thing. So if you have questions, type them in the chat and we will make sure that everybody's tracking along. So let's get started. So here's the agenda. We're going to talk first about just what is hot plate welding, the basics. How does it work? What are the benefits of the process? Where is it used? How you design for it? And then what does the equipment look like? So, broad spectrum of standard hot plate welders and custom hot plate welders, and what are some of the possibilities? All right. So what is hot plate welding? The picture on the right side of the screen is, of the tooling of a hot plate welder. Hot plate welding is a contact joining method, which means the plastic parts are going to come into contact with the hot plate that melts the plastic weld rib on both halves. So there's a heated tooling plate that's in the middle that is machined to match the weld surface of your part, whether that's flat, like it's shown in the picture there, or it's contoured. And you can do both with hot plate. It uses conduction heat transfer because you're touching the hot tool. The heat from the tool is conducting into the plastic, and it's capable of producing strong, hermetically sealed welds, which means they're leak proof. They hold water, they can hold air. They don't have to. They can be used for non-hermetic applications, but they're capable of that. So here's a video. What you just saw there is the hot plate coming forward, the parts coming into contact with it. They come off of the heat plate gets out of the way, and then the parts come together and are held under force to bond together. Great. Thank you, Juan. All right. So let's look at this step by step. First, you load the components. You can see that we have upper press tooling, lower press tooling. You put a component in each half. In this example, it's shown vertically, but there are instances where you have the hot plate welder sideways. So you load a component in the right-hand side and one in the left-hand side. And then you have a heat plate that has heated tooling on it. And that heated tooling, like I said, is machined to match the parts. And then you bring the heat plate in between the two components, touch off. You're actually touching on, like, the whole weld surface is contacting that heat plate so that we get good conduction. Once it's melted enough, we open and then come together under seal, where we're putting force on those parts to let them bond together. Once they're bonded, then the press opens up and you've got a welded assembly. Is that clear? Is there any questions about that before I keep going? Okay, we're going to keep going. If you do have a question, please put it in the chat. So there's two main critical parameters with hot plate welding. And really, these are the same critical parameters that you have with most joining methods. You need heat and you need pressure. You have to get enough heat into the weld joint to melt it sufficiently. And then you have to get enough pressure on those two components coming together so that the material bonds across the weld. So how do we actually control that? Well, we have a heat plate temperature that we set, and it can be different for different materials, different applications. It could be 500 degrees Fahrenheit, 600. Sometimes we do go up to 850. You can go quite hot, but the higher your temperature, the faster you're going to put heat into your joint. Next, melt time. So how long do we spend with the parts on that heated tool? That is allowing that heat to soak into your weld rib. And open time. So when we remove the parts from the hot plate and get that out of the way and then bring them back together, that is your open time. That whole time you spend open and then closed. And your goal is to minimize that open time as much as possible. because the second you pull your parts off the heated tool, they are cooling down. And if they cool down too much, you can get a skin over that weld surface that causes a cold weld. You'd have a little skin on both sides that when you bring these parts together, they don't weld. Like think of your oatmeal or cream of wheat or soup, even for that matter. Like you cook your soup, and then if you have it sitting in the bowl for too long before you start eating it, there's a little skin that forms on top. The same thing happens with plastic. Next, on the pressure side, when we're bringing these parts together, we can control weld depth. So when you bring these parts together, when they first touch, we'd call that zero, like seal zero, when they're just touching, but you're not really applying much load. Then everything that you do after that, like maybe you're pushing 10 thousandths or 20 thousandths deeper so that these parts are squeezing against each other, that is your weld depth. And the more weld depth, you would think, is more force, right? Well, we can also control the weld force. So you can monitor depth and say, I want 500 pounds of force, and the welder will bring those parts together and then put 500 pounds of load on them, which is going to cause the parts to go deeper. So we monitor depth, weld by force, or weld by depth, monitor force. You can do either. So what are the benefits of hot plate welding? It creates a hermetic seal, as we've talked about. So you can get leak-proof parts. You can get, everything leaks. If you're a leak test person out there, everything actually leaks, but you don't lose water from the joint. There's a certain leak rate that's really, really small. You get a strong, robust weld. With hot plate welding, we always target parent material strength, which means if you're going to tensile test these parts and yank them apart or do a burst test on a pressure vessel, it better break somewhere other than the weld. If it starts to crack somewhere else, we know that the weld is stronger than that parent area of the part. And if you can't, beat that, then you can't have any stronger of a weld. Also, because it's not a vibratory process, there's no particulate. So there's no little dust or, plastic fragments going everywhere inside of your assembly, which is good because then it can be used in clean applications. And there's minimal risk of part marking. So you can see there on the screen, hopefully, there is it's like a leather wrap. That's actually a glove box door. So we have this nice, beautiful leather wrap on the outer surface where the customer is going to see that inside of their car, and it's in front of the passenger, and it better not have any marks or scratches or dents, from pressure or anything like that. So it's a hot plate is great for those applications because it doesn't mark the A surface. So what materials can you use with hot plate welding? So some good examples. Polypropylene, very common material in lots of different welding applications. ABS, polycarbonate. You can kind of read down the list there. There's a whole host of different thermoplastic materials in hot plate welding. Thermosets, you can't weld thermoset because those would burn when you try to reheat them. Now, contrast that with a couple materials that you want to stay away from if you're hot plate welding, both nylon and PBT. Those materials are extremely sticky. So when you bring your plastic parts into contact with the heat plate, everything's fine. As soon as you pull away, with nylon and PBT, you are leaving material all over that hot plate, and it makes a mess, and your hot plate builds up this material over time. You don't want to do it. Trust me, stay away from nylon and PBT with hot plate welding if you can. Any questions so far? Kind of going a little bit fast. Do you have any questions?
No, I'm good.
Okay. So you might be asking yourself, okay, nylon and PBT stick. What about some of the other materials? Aren't they kind of sticky? I imagine you're putting a plastic on a hot plate, isn't going to stick. Well, we use coatings. And we have a video here that's going to show you some of the different coatings that we use. We have Teflon-based coatings, and we have chromium-based coatings. If you know anything about Teflon, there's kind of a temperature limit to it. If you heat it above like 600 degrees Fahrenheit, the Teflon is going to start to break down. And so we don't want to do that if we're using these in hot tools. So that's great for lower temperature applications. On the flip side, chromium really only starts releasing material very well once you get above that threshold. So in this video, you'll see two of the same parts being welded with the different coatings. And these are both polypropylene parts. This is a pressure vessel. I think it's a degas bottle. What you'll see here is the chromium side, because it's a hotter, finishes its melt much faster than the Teflon side. And what this is generally showing, in addition to the fact that the two different coatings can both weld plastic parts, is that when you have a higher temperature of 725 degrees Fahrenheit versus 500, the cycle is a lot faster. But there's also some trade-offs. We're not soaking the heat into the weld joint quite as deep because it's heating quickly. It's like searing a steak versus letting it, heat up slower. Okay, so now we're going to get into some applications, and Catherine is going to take it from here.
Yeah, so like Jason said, I'm Catherine. I'm an applications lab engineer here at Xtoll. My team is the team that does all the prototyping work as well as processing and production machines and equipment. That being said, we also do a bunch of other stuff with testing and things like that, but I don't want to bore you with how awesome my job is. So if you have any questions, feel free to reach out anytime. But just to kind of give you an overview on some of the applications we've dealt with in the past. So we do a lot with under hood components. Like Jason mentioned, the Degas bottles, we'll do fuel filters, washer tanks, air ducts, basically things that you'll find under the hood of your car. Some benefits of hot plate welding for these applications are, like Jason had mentioned before, that they can have high pressure applications though. So we shoot for parent strength material with most applications, specifically with tanks, because no one wants their tank to blow up right at the weld that we created. We want to shoot for parent material strength. Not that these parts ever see that high of pressure, but still you can't do better than parent material. So that's a really strong benefit to hot plate welding. Another thing is the hermetic seal. You don't want anything leaking out of the tank really at any pressure, but having things leak is not ideal, specifically with underhood components. So that's a huge benefit. And again, no particulate. Specifically with fuel filters, no one wants any sharp plastic or any particulate getting stuck in their fuel filter. So it's a very clean process. Other things that we touch are any sort of interior trim. There's a glove box picture on the right, so we do quite a bit of those. We also do like center consoles, things like that. There's going to be a video that you'll see a little bit later of a massive center console. So anything that is a surface. There's no part marking with our tooling, or minimal part marking, depending on how we have to grab the parts. But anything that's a surface, we protect with our tooling so that there's nothing that your customer will end up seeing from the welding process. It creates strong, robust welds. We can also create hidden welds, which again is really big with a surface parts. That's a huge advantage of our tooling, that we can get in tight areas with our hot tools and end up hiding the weld entirely. We've also been doing a lot of battery electrical things like that. Again, strong, robust weld. You don't want your battery splitting apart in your vehicle or wherever it goes, any sort of fuel cell. A hermetic seal, you want to make sure that nothing's leaking out of the battery into heat-sensitive PCB areas. It is also safe for heat-sensitive components. We'll talk a little bit more on how to design for that down the road. And then no particulate. We also touch a fair amount of medical applications. Benefits are, again, hermetic seal, no particulate. And then we can also make our hot plate welders clean room safe, which specifically in medical is a huge deal. Our equipment is safe for it, as well as the parts that come out of our equipment are then safe for it. There's no contamination of the weld area. Again, pharmaceutical filtration, clean room certified, no particulate, hermetic seal, all those great things. One of the other benefits of our hot plate welders is that we can do stack welding. So that means we can layer the same weld profile on top of each other over and over again. We've done as little as 2 parts on top of each other, which is what I would consider a normal hot plate weld, all the way up to 40. And then we're even striving to do more than that. So our logic for our hot plate welders allows us to do that with precision and accuracy, creating the same positive weld all the time. So next we're going to get into the design guidelines a little bit. I'm just going to kind of go through the broad overview. It's a lot more specific than probably what we'll touch on, but you can visit this link to kind of get more in-depth ideas on what you need to look for in your weld design. As well as, again, feel free to send your data over to our applications lab. We'll take a look at it. We'll make a report for it, tell you what you need to change, how you could improve it, especially if you need a certain strength out of your assembly. Or a specific visual appearance, things like that. We can give insight into those things. So just a basic weld rib joint design. The first thing is you need to have a weld rib. That being said, the way that the process works, like Jason outlined, is that some of the material is melted off. And then when the parts come together, some of the material is squished out. So we need to be able to have the parts designed to compensate for those two things happening. So you'll see there's the dark red and then there's kind of the lighter orange color. Those signify the material displaced during melt as well as the material displaced during seal. So we need you to design in that material so that we can actually put the parts together in actuality.
Juan asked, do our stack weld machines do its work in a one-step process? So we actually, it's a sequential process. So you take two parts and weld them together, and then you add another component, and then you add another component, and you can kind of keep going like that. We have built, and like Catherine mentioned, you'll see a center console welded, and that is doing two welds simultaneously. It's putting the decorative trim on either side of the center console, all with one step, and you'll see what that looks like. But as you can imagine, if you were going to weld, 40 parts of a stack, that would be 40 hot plates, and you'd have a massive machine. So it's a sequential process.
I used the word indexing the other day, and I
Yes.
really like that description. It indexes down,
Yep.
And then it does all the math to be able to compensate for adding another layer into the weld. It's a really interesting process to watch. So again, these are just kind of the initial guidelines for how to design your weld rib as far as compensating for the seal and then sacrificial melt, as well as a minimum recommendation for weld rib width. Again, depending on what you guys need, you might need to have more material overlap compensated if you imagine your parts are going to be really warped, or you might need thicker weld ribs because you have a really high burst spec. There's a case for everything, so if you have any questions, shoot your data over and we'll take a look. I mentioned a little bit earlier about how we can weld with heat-sensitive components like PCBs. This is a really important, do I have to click it again?
Mm-hmm.
Okay, sorry. This is a really important dimension to take into account if you have any sort of internal part geometry, external skirt, internal components. So we need 1.52 millimeters or 60 thou of clearance from those components. That allows us the room to be able to get our hot tool in and not wipe either side, whether it's a component on the inside or a skirt, to make sure we don't interfere with those. Obviously, if you hit your PCB with a hot tool, it's going to crunch, and nobody wants that. So This is a critical design guideline to have in order to use internal components like that. I will say that if you want shielding from any of your internal components, we do require a larger gap so that we can actually get insulation in. But just as far as general, not coming in contact with anything, this is the number to go off of. So this is kind of a design recommendation as far as how to design your joint if your parts are at an angle. Obviously, we best case scenario get this vertical up and down approach. That is best case scenario, but depending on what you're doing, that just might not be possible. If it's not, we shoot for this middle design. Again, not ideal because you can't transfer the load on the angle as easily as you can up and down. But a key note here is that your weld ribs, although they're at an angle of each other, the weld surfaces are parallel to each other. So you can see in here, they're going to come together and have equal amount of melt displaced on either side of the weld rib. On this case on the left here, We do not have that happen. So what would happen in this case is you would get a bond right here, but by the time you finish the seal portion of the weld process, you might not even have these parts touch. So your whole part is going to be sitting, you know, partially open, and then you're going to have a really weak weld. It's probably going to leak. It's just not a great idea. You can also get a cold weld. In that case, it's going to seriously compromise the integrity of your weld strength. So again, we shoot for what's on the right, but if we have to, what's in the middle is it's doable. We've done it plenty of times.
Mhm. All right. So now, if first of all, are there any other questions regarding hot plate joint design? We can't probably go into specific details of your application, but as Catherine mentioned, if you want us to take a look at it, we offer that service for free. You can get in touch with us, or you can get in touch with your Xtool salesperson if you have one already, and they would be able to get that information over to our PDC where we can do that evaluation for you. So let's look at the hot plate welding equipment. There's a kind of a wide range of different hot plate welding machines out there. For example, on the left, you can see, not this one. There's actually two hot plate welders here. It's a smaller modular hot plate weld system, pneumatically driven. And then on the right, this is a rapid conductor hot plate welder. It's one of the most sophisticated hot plate welders out there. It has 3 servo axes. It's the machine that you saw in the video earlier. And we'll talk through the differences here. So 2 different motion types. Yes. Oh, thank you. Is there a limitation on total weld rib length, or is it just limited by clamping pressure? There is not a limit on weld rib length. We'll talk about it in just a second, but we can weld huge parts. And so if you have, a weld rib that's going around the perimeter, and maybe it's doing a spiral all the way to the center, doesn't matter. It's fine. We can weld it. We'll just build a machine with a stronger press so that it can overcome the forces that it needs to actually weld those parts. So no limitation on weld rib length. Thanks for that question. Okay, 2 motion types, pneumatic and servo. And if there's anybody in the room that says, well, what about hydraulic? Yes, there are some hydraulic hot plate welders out there. The pneumatic side is typically how those all would work. So pneumatic, you have to have hard stops, which are physical, mechanical blocks or things that cause the tooling to hit the other tool on another stop to control your depth, to control all of that. Because pneumatics don't have good positional control. Any pneumatic cylinder has to have, has to hit at the end of its stroke. So that's what hard stops do, is they control the position. And then if you want to make an adjustment on how deep you're welding, you have to adjust those hard stops, whether you shim them or whether there's something that you can twist, which threads them up or down. And you make sure you do both sides, that kind of thing. So those are hard stops. They also typically will use an electronic pressure regulator to control the amount of force coming into the cylinder in the first place. These pneumatic welders are awesome for simple welds. Think like little ports being welded onto a larger part, or maybe 2 halves that are coming together of 2 ports. They're great when you're welding multiple simple components onto one part. So take an air intake duct that has multiple ports on it. You can put that part in here and have 2 modular welders welding this, parts on at the same time, or you can do it sequentially if you want to do it that way. Lots of options. They're very versatile. Servo, on the other hand, doesn't use any hard stops because a servo motor is capable of precise control of its angle. So you can spin really quickly to an exact angle, and if you know the angle of your ball screw thread that's spinning and causing the platen to move up and down, you can figure out exactly where you're going to be when you want it to be there. So you have precise control, like within 1,000th of an inch of where you go. Plus they have torque feedback, so you can use that to calculate your force that you're applying to the part. So as I mentioned, they have precision control, fast cycle times. They move much faster than pneumatics. And because we can control position so tightly, when you open away from your heat plate, you don't have to open all the way back to your load positions. You can open just enough so that the hot plate can get out of the way, bring it back together. So servo welders are great for complex welds, large parts, large welds, and as we've talked about a few times, stack welds. So with stack welds, we mentioned that we have one that's doing 40 welds, so 40 components being welded on top of each other, one after another. And as you can imagine, if you had to program the positions that the press needs to move to for each one of those, that would be kind of a nightmare because there's a little bits of variation, whatever, in your parts. And by the time you get to the 40th weld, you probably wouldn't be bonding anything together. So what we did is we set up a logic where the upper and the lower touch each other before actually melting anything. And it detects when those two parts touch and uses that and does the math and says, okay, based on where these are touching, now I know my positions for the rest of the weld. Does that the next cycle, touches them together, adjusts everything accordingly. So we could weld 40 parts, we could weld 38, we could weld 60 parts. It doesn't matter. We could just keep going because the welder is reprogramming itself every cycle. So here's the rapid conductor. That's one servo-driven hot plate welder. We also have a compact fusion hot plate welder. This is servo-driven as well, but it's a much smaller footprint. That machine, the actual tool in there is doing like a 6x8 inches, 6x8. And it can be benchtop. That one's shown on top of a machine frame, but you could actually take that welder and put it onto a different bench. It's a pretty small, compact machine, hence the name, compact fusion. Here we're going to see a video of, let me hit play so it starts spooling for everybody. Did it start? Okay. This is a servo-driven hot plate welder that is based off of the rapid conductor platform, but you can tell that there's a robot that's going to help load this. So okay, so here we have the center console that's loaded into the center of the tooling. It is, it's got air ducts in it, and they have the pocket that you would put things into your center console. And then what you'll see is this person's going to load the decorative trim on either side, and then the tooling will actually rotate because it has auto tool change. So it's recognizing the part and saying this is the other version, and so it needs the other tools. So take a look. So you can see there, the tooling is coming in and pulling those decorative panels off. Now you have two heat plates coming forward and everything accordioning, yeah, together. And then now it's coming together to weld the parts together. So there's a stack weld simultaneous. But I don't know that you'd want to do too many more than that because it gets pretty complex to have multiple heat plates all in the same direction of travel. I'll let it finish. Ta-da! As you can tell, we can do customized equipment. Something we didn't show on the screen, large pallet welders, like 4 foot by 6 foot plastic pallets where we're welding the top to the bottom. huge parts. The welder, he just jumbo size everything. Like everything is just that much bigger. But we're doing it. Modular pneumatic welders, we saw a picture of those. Robot fed welders, we saw that. Independent 2-up welders, we didn't see that, but that would basically be like 2 welders side by side, smacked together and like joined like a Siamese twin is joined together. So it's like they have independent control and press motions and everything on either side. Multi-stack welders, we've talked about that a bunch. You weld a bunch of parts on top of each other. 6-up welders on a rotary dial. We've done that before where we have 6 identical parts all being loaded onto a dial. Operations are happening to them. They get to the hot plate weld station. The hot plates come in, all 6 of them. They do their weld, all independent of each other, and then it continues on to do like leak testing and whatever else. 2-up collaborative welders. Picture 2 welders that are side by side, not joined together, but like in the same vicinity of each other. And then there's like conveyor systems or robots in front of the 2 welders that are feeding parts and taking out welded assemblies all together. So there's one line of incoming components and one line of finished components going out, but 2 welders doing the job of like together and more. So lots of different options for hot plate welding equipment. Okay. I'm glad you guys all hung with us through that technical glitch. That is the content of our presentation. I hope we didn't go too in depth, but if you have in-depth questions, we would love to hear them. So throw them into the chat. What are you wondering? What didn't quite come through clearly? Let us know, and then we can answer those. On the screen, you have both of our email addresses. So if you need to get in touch with us after this, you can go ahead and do that. We'll be sending out a follow-up email later today, or maybe it'll be tomorrow, with the link to watch the recording of this webinar, which will be fixed. And we will also be sending out the slides, a PDF of all of the slides that you saw here. And so you can distribute that amongst your organization. You can also go to our website to get this stuff to watch later. Here's a question from Jamie. How do you ensure the displaced material does not break off due to thermal shock vibration? Good question. Do you know the answer to that?
Well, I may have some sort of an answer. So the way that we program our hot plate welders when it comes to the steel portion, because your flash is actually created during the steel portion of the assembly, right? So when they come together, we actually tell our welders to slow down before the parts come in contact with each other. If we didn't do that, and if we operated off of something like hard stops, when the parts smack together, that flash would just squirt all over the place. But we actually slow our welders down. We can slow it all the way down to 1% of the speed. Typically, we do between 10 and 12. But so we have it come full speed until they just barely touch, and then slowly press together. So that creates a really nice, uniform, visually appealing flash ring around the part. If they were to smack together, like I said, it would create jagged flash. You can get that a teeny tiny bit with high glass content in your plastic, but it is nowhere near the same flash or particulate that you would get with like spin welding or specifically 5 welding.
What you see happen, and I'm drawing on this slide here, when this material comes into, actually I drew this in the wrong spot because this red material has to go somewhere, right? It goes this way. So you end up with what we call the dog bone, because when you bring these together, it looks like a dog bone. So you get flash that sticks out to the side. If you were to melt all of this material away, you have all this material that has to go somewhere. So it's all going to go this way. And so as you can tell, as you get deeper, the flash just gets further and further out of the side, but it kind of wants to ball up and stay with your weld rib.
Beautiful. Jamie put this.
Yes, thank you, Jamie. That's on our website. What he just put in there is on our website. And if you go here, that's where you would get to those design guidelines. That's the dog bone.
Your drawing was beautiful.
Thank you. I do what I can. I'm gonna erase this now because it's ugly. What is the typical cycle time for the whole operation for for example, a welding a cover to a battery case. Okay, well, scrolling. Oh, I'm scrolling the wrong, this way, this one. This cycle is, let me scrub forward a second. Unload. Okay, bat comes in. 1 apple, 2 apple, 3 apple, 4 apple, 5 apple, 6 apple, 7 apple, 8 apple, 9, 10, 11, 12. That was about a 12-second cycle. Not including load and unload. That's actually very fast for a battery. 12 is probably the fastest you could go. You could get it, you could spend more time doing seal or whatever. It might be 20 seconds long. That's pretty typical for that kind of application. As you could tell for like the bottles, when we did the chromium Teflon comparison video, the like a bottle like that takes quite a bit longer because it's much thicker weld ribs. Are materials containing fiberglass usually not suitable for hot plate welding? So yes, we can weld materials that have fiberglass in them. It is an abrasive material, and so it's going to wear on your hot coating. So chromium, yes, would be a better solution typically. If you had a material that didn't behave very well with chromium, you can do Teflon. And actually what you see in the left-hand side is a Teflon sheet. We can do coated tools where the tool itself is like coated in Teflon coating or in Teflon coating, yeah. Or you can have this Teflon sheet that's replaceable. In fact, this welder did that. So there's a roll of Teflon paper behind, and after a certain number of cycles, the machine would automatically index the Teflon coating out. You would cut it off, and then you'd keep going because the Teflon paper itself was starting to get worn out. So yes to both things. Yes, fiberglass can be hot plate welded, and yes, chromium can help, but you can also do it with Teflon. What's the expected life cycle of heating elements and thermocouples? Ooh, good question. It kind of depends on the machine because there's a whole host of different heaters that you can use. Our rapid conductor welders use a split rod heater cartridge, I'm told. I've never actually seen one before. And they last very long time, like years. And then as far as the thermocouples, that I don't have any. Do you have any idea? I don't know. They last quite a long time, but we do, like we've refurbished hot plate welders that have been in service for 4 years or something like that, and have been welding parts like around the clock, like for 3-shift applications. And the welder comes back and, we replace all the wiring and whatever. And in that instance, we would replace the heater rods and the thermocouples because they're probably nearing the end of their life. Thanks, Ivan. What other fastening systems do you use besides vacuum? Oh, yes. Okay. So yeah, in that first video, it's just vacuum holding that part together. Typically, we want to have a mechanical retention of some kind. We'll use vacuum to like hold the part until the safety doors have closed. And then we will have clamps slide in and, grab on some features of the part to keep it in that upper tooling. And then the same thing for the lower tooling. Because with hot plate welding, when you pull off of that heated tool, there's a lot of surface tension and you really want to be holding onto your parts tightly. Otherwise, they will slip out of the tooling, and then they're sitting on the hot plate, and that's not fun.
It's not fun.
Any other questions? Great. Well, thank you everybody for joining. And if you think of a question later, just send us an email or respond to the follow-up email that we're going to send out, like I said, later today or tomorrow. Have a great afternoon. And if you're in Michigan, enjoy the partly cloudy weather. Bye, everybody.